So, with you all, so you can please mute yourselves, and once I start asking, and if I need to ask question, I'll let you guys know. Yeah. So welcome. Yes. In this session, I'll be taking you guys through grid integration of renewable energy systems. So the more or less the challenges and the issues which are currently faced with integrating renewable energy systems into the grid. First of all, before progressing, if I may ask, I'll just ask a brief question. Like, anyone can help with some examples of renewable energy systems? Anyone?
Good morning. We have solar renewable energy system and also hydro renewable energy systems, if that's the answer.
Beautiful. Any other person wants to add to it? That's just a beautiful. And that's common. Anyone wants to add? Yeah, I want you to be lively, so yeah, please give your opinions. Yeah, there's no wrong answer. Put it that way.
So I believe you can also include wind renewable energy system.
Yes.
Wind turbine.
Yes. Perfect. So yeah, you guys have mentioned the major ones. Yeah. So and yeah, very good. So let me jump straight in. Okay, so jumping straight into it. Yeah, as I said, the topic is grid integration of renewable energy systems. Then a bit about myself. Yeah, so my PhD was focused on control strategies of virtual synchronous machines. So this more or less also known as grid forming converters. I'm also a Google certified data engineer, and I'm also a member of the Institute of Engineering and Technology, IET. Also, so some of my skill sets include working with MATLAB and Simulink, PSCAD, Python, and renewable energy systems, and also working on with Google Cloud. And as expected, my interest is renewable energy systems, and that's why we're discussing renewable energy systems. So, and also smart grids, cloud technologies, and grid analytics. So these are my interests. So areas which I would love to work further in the future. Yeah, so going further, yeah, so for today we'll be going about the first aspects will be I'll give you a background on renewable energy systems. It's going to be very brief. So then power system stability, then grid connected converters, then we'll talk about droop, inertia, short circuit level, short circuit ratio, grid forming converters, and then we'll conclude. So just to let you guys be aware, right? It's gonna be like top level. I'm not gonna go in depth because the goal is to make it for you guys to have that broad picture of what's going on this space of renewable energy systems, integrating them into the grid, and to make it also an interactive session as much as possible within the time we have some more or less time constraints. Okay, going further. So yeah, so with respect to renewable energy systems, as you guys have rightly mentioned, we have solar PVs, solar panels, wind turbines, and other renewable energy sources, and we also have biomass and the likes. So the energy landscape is evolving. So the energy landscape is evolving. I having more renewable energy systems or sources coming into the picture. Having more renewable energy sources coming into the picture, and let me just mind this. So we're having more renewable energy sources or systems coming into the grid. So this is for the UK, but it's also an indication of what's going on around the world for most of the developed countries. Like they want more renewable energy systems into the grid. So as you can see, it's exponentially increasing more or less. So by 2050, we expect us like it to be like a lot of renewable energy power coming from renewable energy systems, solar, wind turbines. Meanwhile, for like coal, gas-fired plants and the like, we expect a decline until it becomes zero, more or less. So in short, what's happening is that fossil fuels will be replaced by green technology, more or less, renewable energy systems. Okay, so that's number one. Number two is before going further, so if I may ask, what do you think will be the problem when we have more renewable energy sources in the grid? So any answer, anyone to give any suggestion? What do you think could go wrong when we have more renewable energy systems, so replacing the conventional generators? Any suggestion? Yeah, I said no wrong answers. I want it to be interactive, so you guys should, I'd like to get your opinions. So what do you think could go wrong?
Good morning again.
Good morning.
So I think if we have more renewable energy systems integrated in the grid, there'll be like power overload or a kind of mismanagement of the energy input into the grid.
Beautiful. Beautiful. That's beautiful, and that's one of the problems we're going to be facing. Beautiful. Any other person? Any other one wants to give an input? Yeah, you can.
Yeah, good morning. I'm Yunus.
Good morning.
I think when we have more renewable energy integrated into the system, we have more stable power.
You have
more energy, more stable power in the grid. I mean,
okay. Yeah, thanks for that contribution, sir. Thanks. So yeah, beautiful. So yeah, as you guys have rightly said, like it's increasing renewable energy systems due to their nature, the intermittent power supplies. So sometimes you have the sun shining, and sometimes it's raining, more or less. So the power is intermittent. It's very variable. So similarly for the wind turbines, sometimes it's very windy and you are generating the maximum power you want, and in some cases the wind is not blowing or virtually not blowing, or it's too slow, more or less, and the wind turbines cannot work at that slow speed. So you have that problem of intermittency. So it's variable power supply. So yeah, sometimes it might become too much, or sometimes it might become less than what is required for the grid to operate. So that's one problem, which is related to the intermittency. So with what I'll be focusing on today is looking at it from a different angle. So and this is interesting. So and that problem of intermittency, yeah, it's one which definitely would need like energy storage and other what do you call it, solutions to solve. So but it's a very valid problem, and it's a big problem also, which they're looking at the various ways to resolve that. So but I'll be looking at it from a different angle, which is with respect to the system stability. How does this new technology, solar PV and wind turbines, how do they affect the stability of the grid? Okay, so let's first, power system stability has to do with the ability of the system to regain a state of operating equilibrium after being subjected to disturbance. So more or less, how does the system react to disturbance? You get, so does the system able to maintain stability? Is it able to recover from what do you call it, disturbances? So that's one of the key aspects of our grid, more or less. You get, so we want to be sure that once there's a disturbance, because it's impossible that your system will keep running forever without any disturbance or any form of disturbances. But we want to be sure that once there are disturbances, we are able to recover from those disturbances without much going through much hassle. So, and this is how the power system operates. So the power system, more or less, stability problem can be divided into three. So you have the rotor angle stability, the frequency stability, and the voltage stability. So those are like the three major aspects. So I know, yeah, with increasing renewable energy sources, yeah, it could also be expanded beyond this, but these are the three major aspects which we look at mainly. So first is rotor angle stability, which deals, so these definitions are quite simple, so just for easy understanding. So, and rotor angle stability deals with the ability of our system to maintain synchronism after it's been subjected to disturbance. So the ability for the system to maintain synchronism after it's been subjected to disturbance. Similarly, for frequency stability, is asked to be the ability of the system to maintain the frequency within nominal value after the disturbance. So you want to be sure that after there's a disturbance in the system, is our power system able to recover, and is the frequency within the nominal values expected. So those are things we want to check. If the system is able to maintain that, then we can say, yes, our system is stable. So the frequency stability is good, more or less. So, and similarly for the voltage stability, it's about the system being able to maintain the voltage within nominal values after disturbances. So as we know, disturbances could occur like short circuits. You can have a tree falling on the line. You can have various things happening. You get, so these are things that happen regularly, whether it's abroad or in Nigeria or wherever. So disturbances are bound to happen, and we want to be sure that our system is able to respond appropriately to these disturbances. Going further, as I said, I'll give room for questions and answer at the end of the presentation, so you guys can ask questions as much as possible. And as I also said, if for any reason the presentation should cut, would try and reconnect straight on the same through the same link again. So that should work. Progressing further, okay, so conventionally, so the conventional way of integrating renewable energy systems into the grid has been to employ a technique known as grid following technique, more or less. We call them grid following converters. So for grid following converters, so yeah, I wrote them as RES, which means renewable energy sources, and this means SG here actually means synchronous generators, while this is PCC, which refers to the point of common coupling. So it just refers to the point where you connect your system to the grid, more or less, where you connect your system to the grid. So PCC, point of common coupling. So this is just representative of a transformer. Okay, so for the conventional way of control, what's known as the grid following converters or grid following control, usually the operator just specifies a certain amount of power which they want you to generate. You get, maybe for example, maybe from your wind turbine or from your solar PV, they specify a certain amount of power they want you to generate. So usually this type of designs don't have control for the voltage, and they don't have control for the frequency. You get, so they don't support the voltage control, they don't support the frequency control. However, for synchronous generators, so i.e. the conventional generators, inherently they support the voltage and the frequency. So this is how they are designed to provide support for the voltage and frequency. So how is this a problem? And I have this slide. Let me see. So this is just for explanation purpose. So what happens is that so if you assume that these are all, this is more like a rowing sport, as you as you all know. So if you assume that all these four guys, 1, 2, 3, 4, are supporting okay, like in a sport, while in a sport, when you are more or less you're in the water, more or less, you have 4 of them rowing together to ensure that the boat goes as expected at the right speed, and ensuring that other factors are in place. So if, for example, we remove one of these guys, so if we remove one of these guys, i.e. he stays there, but he's not supporting the rowing, what happens? It becomes more difficult, right, to row. Am I right? Any answer?
Yes, sir.
Yes. So it becomes more difficult to row. Then now imagine a case of 3 of these guys not rowing. They're just sitting down, they're not rowing, and only one person rowing. What happens? It becomes more burdensome. It becomes a lot of burden for the person to roll the system. So it's a lot of burden. Not only that, if there's for example, a wave coming in, then the probability that the boat would survive it becomes very, very low. So there's a high chance that they're going to all sink in the boat, because all the burden is on one person. All the burden is on one person. So this is the same way the converters following the grid following converters, this is the same way they affect the system. So if you have more renewable energy systems employing these grid following converters, grid following algorithm, more or less, then you have less generators supporting the grid. So you can assume this synchronous generators to be the guy who is rowing, the only guy who is rowing, while the renewable energy sources to mimic the guys who are not rowing. They're just sitting down there, they're not rowing. So as you see, if you're having more of renewable energy sources which are employing this particular type of control, i.e. grid following control, then the burden is on the synchronous generators, and the system is less likely to survive a disturbance. Now you get it, right? You get the analogy? Okay, so going further. So what we're looking at now is that for small percentage of renewable energy sources in the system, it's easy relatively to manage it, i.e. it's easy to manage it. Like if you have like 20 people rowing and one person not rowing, it's easy to manage it. But in the case where you have 3 people that are rowing, 2 people that are not rowing and only one person rowing, then it becomes burdensome, and the probability of the system surviving disturbances becomes the chances of surviving the disturbance becomes very, very low. So, and that's where the concepts of grid forming converters come into play. So grid forming converters, from the name, what it simply means is that they're able to form a grid, more or less. And what is important really is that they provide support for the voltage, and provide support for the frequency. So as I earlier mentioned, one of the key aspects of power system stability is voltage stability, frequency stability. And to ensure this stability, you have to control them in a suitable manner, control the voltage, control the frequency to maintain the stability of the grid. So grid forming converters are also known as virtual synchronous machines. So and they get this name because they try to mimic the desirable characteristics of the synchronous generators, which includes supporting the voltage, supporting the frequency, ensuring that the system is stable after a huge disturbance. So going further, so yeah, this is just more or less like same picture. So i.e. in this case now, with grid forming converters, everyone is supporting. All the renewable energy sources are supporting the grid. So that way, we are not, by having more renewable energy sources, our system maintains stability. Our system maintains stability because everyone is supporting the grid. Everyone is rowing, so everyone is supporting the grid to ensure that the system is operating as expected. So going further, I'll begin with a concept known as droop. Anyone knows about droop control here?
Nope, it's new to me.
Yeah, okay, no, okay. Any other person? Okay, I'll just jump straight into it here because of time. I said time constraints. I'd love to get more opinions, but yeah. So, but yeah, the concept of the droop control, more or less, is one whereby we try to reduce the frequency as the power demand increases. So as the power demand increases, or as power demand increases, so active, for example, so this goes for active power and also reactive power. So we have both of them, active and reactive power. So usually there's proportionality for transmission lines, more or less, or at the transmission level. Usually the power is proportional to the frequency. Similarly, the voltage proportional to the reactive power. I won't be going into much details as to why this is the case, but it's just good to note that power is proportional to frequency, at the transmission level, and also reactive power is proportional to the voltage. So I've also dropped a reference here, which you guys can always go back to, and is to learn more about this group control and the like. So, but what's key here is that the way the power system is controlled is such that once there's an increase in demand for active power, the frequency is expected to drop slightly. So, and there is a range which the frequency.
Thank you, sir.
Thank you, sir. Okay, so continuing. Yeah, so there's a probability that I realized that it's only 40 minutes it allows, but would reconnect again if it goes off. Yeah, so yeah, so I think that should work out well for us all. So yeah. Let me turn back to this. So as I said, so the way the synchronous generators work, i.e. the power system works, is such that as the power demand increases, for example, active power demand, as active power demand increases, the frequency drops proportionally. So, and why is this the case? So one might ask, like, why not ensure that the frequency is 50, for example, all through, for example, like regardless of the increase in power? But what happens is that if you try to if the system is designed in that way, i.e. each generator is trying to maintain 50 Hz, each generator trying to maintain 50 Hz. So, and as you expect, you have several generators working together. So what's going to happen is they're actually going to fight each other, because each generator wants to maintain 50 Hz, each generator wants to maintain 50 Hz in its own way. So it's going to lead to instability in the system. It's going to lead to instability. So rather than ensuring that they maintain 50 Hz, so they maintain the frequency at the reference value of 50 Hz, or which is more or less 1 pu, what happens is we reduce the frequency proportional to the active power demand. So this is how it works. So this is the equation. So I won't be going much into the equation, but what you need to know is that this frequency is the measured frequency. The F naught here is the reference frequency. So, let me call the reference frequency or the nominal frequency, which, for example, in Nigeria is 50 Hz. So 50 Hz, while KF here represents the droop coefficient. So just call it droop coefficient for frequency. So droop coefficient, and this P is the measured power. P here is measured power. So definitely you can look into this later on. And I said, I've provided references here for you to go back to if you want to learn more about droop control and how it works. So, and the same principle applies for the voltage also. The same principle I mentioned, it applies to the voltage. The voltage is regulated proportional to the reactive power. So as the reactive power increases, we want the voltage to drop proportionally. So the voltage drops, the reactive power as reactive power increases. So this is how the power system frequency and voltage are being maintained. So I'll just go a little deeper. So I did a simulation here using MATLAB, and for this simulation I used 0.1 pu, so per unit, so more or less so 0.1 pu for the as reference, as the droop, more or less. So I want the voltage in this case to change between 1 pu and 0.9 pu. I guess everyone has an idea of what per unit means. So, but yeah, am I right?
Yes.
Yes. Okay. Thank you very much. So per unit, so just per unit. So usually this might vary. So in some at different voltage levels or in different countries, you will have different policies with respect to the voltage deviation expected. So in this case, now I said I use 0.1 pu. So for example, if the national grid has informed you that they only want the deviation to be between 0.9 to 1 pu, for example. So you can design your system such that at 1 PU, you can see when the voltage is at 1 PU, you are not generating any reactive power. But at, for example, 0.5, once your voltage drops to 0.95, it means at that point you're already generating 0.5 PU of reactive power. And once you are generating the maximum reactive power, that means your voltage should already have dropped to 0.9 per unit. So, and I've also illustrated it here for easy understanding. So as your reactive power increases, your voltage is going to drop proportionally. So at maximum, when you are generating the maximum reactive power, the voltage should be at the lowest value allowable, so which is 0.9 PU in this case. So as I said, this could vary. Some places you might only want the voltage to drop for 0.5 PU, so you can what do you call it, change or tune your droop proportionally. Okay. So the same concept works for the frequency droop. The same concept works for the frequency droop. Hello, are you guys with me? Hello?
Sure.
Yeah, okay, good, thank you. So the same concept works for the frequency droop. So RE as the frequency drops, for example, or as the active power increases, more or less, as the active power increases, the frequency is expected to drop proportionally. The frequency is expected to drop proportionally as the active power increases. So in this case, again, I use a different droop. Here is 0.01 PU, which is the standard here this is standard in for example, UK. In some other places might be different, in Nigeria might be different, and other places might be different. But here in the UK, it's 0.01 PU, and I just use that. So, and what this means, you can see here it is varying from 1 to 0.99 PU. So at the minimum, we want the frequency to be 0.99 PU. So as the minimum value, i.e., once you're generating the maximum active power. So, and explaining similarly from here, you can see as the active power is increasing, the frequency drops proportionally. So, and yeah, this is the equation. So I said you can always go back to the equation. You can always go back to the reference I provided to get better understanding on how it works. Okay, so we'll be jumping into inertia. So anyone knows about inertia? Or heard the concept of inertia before? Anyone? Okay. Just before I jump into the inertia, so I can realize that the remaining time here is showing 1 minute. Yeah, so let's try to reconnect. I think that should work out. Let's try to reconnect. So because it's going to stop now. So it's going to stop in about less than a minute. So let's all reconnect again. I think it should allow us to reconnect, and